engineers. This is Deeman. So I'll start with the famous quote. Necessity is the mother of inventions, as already one of my friends stated. So this is what I'm going to present on. Design of pneumatically assisted shifting system for Formula SA racing applications. Okay, so the journey, we'll be going through the introduction, the final goals I set, and the design phase, the testing, the flaws that I encountered, and then go back to the design phase, and then testing again. This is a loop, and then go back to results once I achieve the design and final goal. So introduction, I'll just skip this part because it teaches you. So the gearbox which we're going to use is a sequential gearbox of Honda CBR 600. So the previous design, as in why do we need a new shifting system? The previous design, as you see, is like this. It's a clutch integrated shifting mechanism. This is a butterfly valve. So during the downshift, the driver clutches and shifts it down, and during upshift, he just pushes the lever. So that was the previous design. That was the previous shifter. So yeah, as in this, the driver basically, whenever he turns, whenever he take a turn, or whenever he needs to shift down, he needs to take out of his left hand from the steering wheel, and then shift, and then go back to his steering, and that's what happens. So basically, we're talking about racing here. 0.1 seconds is also a big deal. So the disadvantages in this is it takes 2 to 3 seconds for the gear shifting. So the driver takes off his hand from the steering wheel, shifts, and then go back. And maneuverability issues while cornering it, etc. Same, the steering control, won't be having good steering control. The space constraints, because you have a separate lever here inside your cockpit. So the cockpit is smaller, so the driver comfort is at risk. Now the design intent, what am I focusing at? Driver hands on the steering wheel on points of time, because that is very much important in your cornering. Less weight as possible. Of course, any race car you need to have as less weight as possible. Fast and accurate shifts. Implementation of launch control. Launch control here is an automatic system where your peak in the RPM versus the top curve senses, and you can shift it automatically. So that is what I want to implement. So this is what I start off with. I have a Honda CBR 600 engine, 600cc. Force for each shift is 120 Newton, push or pull for the upshift, pull for the downshift. Travel of 15 mm with a lever length of 35 mm. This lever length is adjustable. So at the end, if I have a lever length of 35, I need 15 forward and backward. That's what my design constraints are. So here to start off with, I mentioned it there. So I basically have two systems. I can go with electrical, in which I can just use direct solenoids and then put them on it, so that whenever I press a switch, now the solenoid gets activated and pulls my lever. Otherwise, I can go with pneumatics, where pressure air is used to push in a piston, and the piston is used to push the lever. So, but the first case, since we are dealing about a race car here, and the race car has a very tiny battery. So, if you directly activate a solenoid, which can pull a 120 Newton force lever, so that would drain off your battery very fast. So otherwise, if you have a very good alternator, that would require your engine power to keep recycling it. So this is the first iteration I've done. So in this case, what happens is just pneumatics, no electronics into it. It's normal compression, normal 3x2 valve, push buttons on the steering wheel. So I have two push buttons on my steering wheel, one for the downshift, one for the upshift. So without taking off his hands, he can just push the button and your shift is done. So my problems are, the timings are not coming. I mean, I checked this system up and it's again 1.2 seconds or 1.3 seconds. When before it's 2 seconds, I mean not much of a difference. So I introduced electronics into this now. Electronics, I put a relay switch and then I connected a solenoid. Now this makes my length of wires very small. Now what really happens in that case is, if I have just pneumatics into it, and my buttons are at my steering, but my engines are the rear. So my pneumatic forces should pass all the way through my chassis. So now whenever I push the button, so now the air should travel all the way back. But in case of electronics, it's real time. So it's at the rear, my solenoid is at the rear, my compressor is at the rear, so it's all real time. So this is the basic circuit. The storage tank at 60. Press the button, that gets activated remotely. Done. So this is how it goes. storage tank which is at 4500 psi, air source adapter to bring it down to the inline regulator, and then to the double actuating cylinder. And my double actuating cylinder is something like this, and now I have reed sensors at both the positions which can sense my piston, and then I have a middle reed sensor which is my neutral. Now if I have a Arduino microcontroller to control this shift. So what I say, if this is high, so this can start moving in either direction. So press up shift, it goes forward, and now whenever this reads, the solenoid gets a signal that it reached the position, so now the solenoid stops sending the air. So the shift is done, it reads right back. So it's the same way for the downshift. So this is just the components I've used. That's the tank, and this is the basic circuit, the tank. This is on the static gearbox. The first phase of our iterations were on the static gearbox. We didn't directly want to test it on the working engine, as in the running engine. We didn't want to risk it. So this is the system. We place the reed sensors here. You can see it. The middle sensor is glowing. So this is how it went. You can see the shifter moving there, the gears. The dog gears meshing, and yeah. So the problems faced in my first set of iterations were the neutral issue, because all the high performance engines have 1 neutral, 2, 3 and so on. The neutrals after 1, and if I take any commercial vehicle, it's neutral 1, 2, 3. The main reason is that any high performance vehicle, the first gear reduction ratio is really high. You need high torque at the initially, so the first gear gear reduction ratio is really high. So while just coming back from your fifth gear to neutral position, you didn't want to hit this first gear because you don't want to damage that gear. With that high RPM, you don't want to basically damage that gear. So you basically have neutral gear. But in this case, okay, you have something called a gear interlocking mechanism, because once you select a gear, you should not slip out of that gear. You select second gear, you should be in second gear. So we have cam controlled something like this, I mean, some star kind of thing. So this is what is a cam gear interlocking mechanism. You have a roller here. So now this makes sure that you are in that place till you set the other gear. So what happens is, for the one neutral 2, you have a half small curve there. For the other, you have big spikes. So whenever the rollers here, the tendency of slipping is really high, because manually you can do it, because once you go into second gear, that's okay, you can come back. But in case of pneumatics, the reed sensor can't sense it in between. It's either extreme positions, so you can't do this. So that was my first problem with the gear pattern. The second is, as I said, the interlocking mechanism. Improper shift, that's because of electronics problems, and static engine, because static engine, as in you don't have torsion onto it, and your dog gears are at a particular place, and once they mesh, you can only mesh once. I mean, you need a rotating shaft for the free movement of your dog gears. So leaks are common. And eliminating the issues. To eliminate these issues, the first thing we thought is to change the drum pattern. The drum pattern is 1, neutral, 2, 3, 4, 5, 6. So we will change it to neutral 1, 2, 3, 4. So that way we can eliminate it. The other way to eliminate is we can change the star. As in this, you see the small spike which we are talking about. The others are bigger ones, these are smaller ones. So we can change the pattern of that star. These are the shafts which go onto your drum, and depending on the rotation of your drum, the gear gets selected. So, results and accomplishments. And now now what we did, once we got this thing all done, now we eliminated all the reed sensors. Now we are doing this with the help of timing. As in, we say whenever you press a button, open it for 80 milliseconds. And this calculation we got it from CRO. We connected a CRO and checked the spike from the initial spike whenever it's getting the high voltage. It took 80 milliseconds, actually 60 milliseconds, and this 20 milliseconds we added it extra for the safety purpose. And now we eliminated all the read signals. So now we don't have any feedback. Now it runs on timing. So once our driver presses a shift button, the solenoid gets activated for 80 milliseconds and gets the shuts off. So that way we can reduce the cost, because reed sensors are costly. So that way we can reduce this. And the next, 80 milliseconds, the average shift timing around the IC track which we drove, it reduced from 25 seconds to 19 seconds. That's a phenomenal 6 seconds reduce. Maybe due to different factors also, the differential will change and many things, but significantly due to the pneumatics. It's the first Indian Formula SAE car with pneumatic gearshift without an onboard compressor. This doesn't have an onboard compressor, we just have a tank. So this is the first Indian team. And yeah, any design you need to commercialize at the end. So we are trying to get this commercialized, as in any high-end cars right now are having these pedal shifts. For suppose Civic is having this pedal shift, but in case of Civic, what really happens is there's a gearbox, and now the pneumatic, the high pressurized air, that pushes directly your gear, as in that enters your slot and tries to push this gear directly. But the main problem with this is you need a lot of air, and for that you need to have an onboard compressor. That means it's deriving its power from your engine. So that way your mileage and everything gets reduced. So this doesn't have an onboard compressor, so this is really easy. Acknowledgements, yeah, I've done it before, so I would like to thank Festo India for their constant support. I mean, they sponsored us all through.